Welcome to the final lesson on game theory. In this lesson, I'm going to talk about two sequential games that are a little bit more complex than the ones we saw in the previous lesson. The first of the two games we're going to look at is called the Pirate's Treasure Puzzle. It has a very large number of possible alternatives at each decision point. However, as we'll see, the puzzle can be solved without enumerating all possible alternatives. I'll point out where we kind of hide or discount, I guess you would say, some of the alternatives that are just not likely or logically not likely. So here's the puzzle. There's 5 pirates, all men except the captain. So the captain is a woman, and they're of different ranks from 1 to 5. They've stolen, it was the highest rank being 1, so the captain, she's number 1. They've stolen treasure of 100 coins, which need to be split amongst themselves. Pirate number 1 makes the first proposal concerning how the coins are to be divided. All the pirates, including the captain, vote for or against the proposal. If 50% or more of the pirates vote for the proposal, the coins will be shared as specified by the captain. Otherwise, the captain is thrown overboard and the process is repeated with the remaining pirates. So pirate number 2 would make an offer, and if he was outvoted, he would get thrown overboard, and then it would go to number 3 and so forth. So some further rules here. If a pirate can get the same number of coins by voting for or against a proposal, he or she will vote against the proposal. Assume all the pirates are rational and seek the highest number of coins and do not wish to be thrown overboard. What is the subgame perfect equilibrium? So we're going to solve this, and I'll show this on the next several slides. We'll start from the bottom. So this is sort of the backward induction process that we've used before with some shortcuts. So we're not going to actually draw all the possibilities. There would be quite a huge number because of the number of coins here. There could be many, many different possibilities, but we'll avoid doing that. At the top here, I have the table that shows an analysis of the game. We're going to start at the bottom, working our way up. So pirate number 5 only gets a chance to make a proposal if pirates 1 to 4 have already made proposals that have been rejected and therefore thrown overboard. So pirate 5 would be the only pirate left on board and has I shouldn't say no choice, but the logical choice is to give himself 100 coins, and then of course he would vote, being the only one left, he would vote following the procedures and he would get the 100 coins. So what we've excluded from the game tree is the case where he would give himself 99 or 98 or all the way down to 1 or even 0. None of those make sense financially, and so we just, that was the type of shortcut I was referring to. We wouldn't show that in the tree because it doesn't really make any sense to. So that gives us the bottom row down here. In other words, these 4 pirates have been thrown overboard. There's 100 coins left, and the pirate number 5 gives himself the 100, or proposes 100 coins to himself, and then votes on his proposal. So that's kind of easy. Working backwards, so this row here, so pirates 1, 2, and 3 have been thrown overboard, and you only need a 50% approval to win. So pirate 4 would say, my proposal is I get 100 and you get nothing. And pirate 5 can't do anything about it because pirate 4 is going to vote for the 100, and that's what he'll get. So that's this row down here. Let's proceed with the, no, maybe just one point here. Note that we have discounted the possibility of pirate 4 offering himself 99, 98, and so on. So that's the same issue I mentioned in the first case, because they're just not logical choices to be made, and so we don't bother drawing those into the tree. Okay, so let's continue with this case here. I have that on the next slide. So we're at this case, pirate 3 is going to make the decision. Pirates 1 and 2 have been thrown overboard. And keep in mind, all the pirates have logically deduced this table. That's the assumption of the game. So if pirate 1 takes 100 coins, the other two will get 0, or at least if the pirate 3 offers a plan for 100 coins all going to himself, the other two would reject the offer and throw him overboard. So that's that's not a logical choice. The other possibility is that pirate 3 offers himself 99 and 1 to pirate number 5. Now in this case, again, pirate 5 and 4 know this whole logical output of this table here because they're able to think logically. That's the assumption. And so pirate 5 votes for it because he knows if he votes against it, pirate 3 gets thrown overboard, and then we're into this case here, and pirate 4 would take all the 100, and pirate 5 would get nothing in that case. So all the pirate 3 needs to do is offer 1 coin to pirate 5. It's not a good choice, but it's better than 0. And so pirate 5 will vote for this, and then you have 2 votes for this proposal of 99, 0, and 1. And that would win out. Okay, so we've done the bottom 3 rows of the matrix. Let's continue. Continuing with the analysis, we're at this row here. So pirate 2 is making a decision. Pirate 1 has been thrown overboard. And if pirate 2 offers 100 to himself and 0 to the others, that's going to get voted down. So he's not going to do that. So what he needs to do is figure out how to get one more vote, because you only need 50% of the votes to win. So if he gives 1 coin or offers 1 coin to pirate 4 and all the rest to himself, 99, then pirate 4 is going to vote for it, because if he votes to throw pirate 2 overboard, it reverts to this case here. And in this case here, pirate 4 gets 0. So even though, it's not a good choice, but it's the best he could do. So pirate 4 will vote for this 1 coin, which is better than 0. And then, of course, 3 and 4 will vote against, 3 and 5 will vote against the proposal, but you only need 50%. So that's what would happen if, in this case here. So we need to go back one more step to see the whole picture in the logical flow. The captain, again, she can't offer 100 to herself and 0 to the others because she would get outvoted 4-1. So she needs to get 2 votes from the other 4 pirates in order to win 3-2. There can't be a tie here because now you have 5 pirates. So what does she need to do here in order to secure the votes? So if the captain gets rejected, pirates 3 and 5 know they can be forced to take 0, right? That's this second row down here. So if she gives them both 1, then that does better than getting the 0, which is what they would get if they throw the captain overboard by voting no. So they're going to vote yes. They'll get 1 each. Pirate 2 and 4 could vote no, and they will because they're getting 0. and so the captain would win 3-2, and then this would be the actual outcome. The captain would over the whole thing now because we worked backwards to this solution here. The captain would offer herself 98, pirate 0, pirate 2 and 4-0, and pirate 3 and 5-1. These two would would vote yes because they know they would lose and get 0, reverting to this next case down. Okay, so that's the solution to the pirate puzzle. I have one more puzzle following this in this lesson here. The centipede game, and I'll give you a link to this, tests the limits of backward induction approach. We'll see that we come up with a non-intuitive solution. I'll do the analysis on the next slide. The game involves two players, X and Y. At each turn, one of the players has two choices. Either take the money, and there's a $2 gift at each decision point, as well as split the existing pot between the two players, or the player can, what we call put here, basically add the $2 gift to the pot, and then you go on to the next decision point for the other player. The pot starts with 0. To be clear, the $2 at each decision point that's inserted comes from a source outside of the two players. It is gifted at each round of the play. The game consists of 100 rounds. On the last round, if player Y puts the $2 gift into the pot, the game ends by splitting the money evenly between two players. That's what's shown here. They would each get $100. And the game tree is shown here. So let's just go through a few of these. The pot starts at 0. So player X can split the pot, which is 0, so there's nothing to do there, and take the $2. And then the game would stop at that point. But if there's ever a take anywhere along this tree, the game stops. So if player X took a take here, X would get 2, Y would get 0, and the game would stop. The other option is player X puts the $2 that's inserted into the pot, and then Y can either split the pot and take the $2, and that would leave a payout here of 1-3, and the game would stop. Or player Y can take those $2 and put them into the pot. So now you would have $4 in the pot. Then it alternates. Player X can split the pot, so 2 and 2, and then take the $2 that's inserted, and so the payout would be 4-2. Or player X can put the money into the pot, so there would be 6 in the pot. And then you go back to player Y, and the game goes on potentially for 100 rounds. And if no one does a take, they both get 100, which seems like the reasonable solution for both of them, right, to get $100 here. But when we do the backward induction, we'll see that that's not what happens. We'll look at that on the next slide. Okay, so as you know, backward induction works from the bottom. So starting at the bottom of the game tree, player Y gets a higher payoff, 101, by taking the $2 that's inserted and then dividing the 198, so that would be 99. So each player would get 99, and then player Y would get the $2 added. So it would make sense for player Y to do a take here and not let the game go to this 0-0, 100-100 solution, excuse me, at the end. The same result follows all the way back. So if you're here, player X would do the take, basically splitting the 196. I didn't draw that in here, but basically splitting the 196, so 98 each, and then taking the $2 that's inserted in. So if you're looking right here, the game would stop and you wouldn't go down. And that filters all the way back to the top here. So if you're looking at the top, when you first start, player X looks at both players, of course, can analyze the tree as we're doing here, and we assume they have this knowledge of what we're looking at here. So player X can take and get 2, or if player X puts, he or she knows that Y is going to do it, is going to take, because Y would get 3, which is better than 2, but X would get 1, which is less than 2. So X would take on the very first round, knowing how this game is being analyzed. So even though both players would do better by, making a small sacrifice as they go along here for that $1, they could both get $100 if they let the game play out to the end. So this is showing that if we do a very strict backward induction, we get a non-intuitive solution. The solution would actually be player X taking the $2 that's inserted and stopping the game right there, and player Y would get 0. So let's see if there's some way of fixing this, which seems like a problem. Let's see if we can fix that on the next slide. As we saw, the backward induction result depends on treating each player's payoff as equal to the player's monetary receipt. That's the problem. Players may, however, care about more than their own immediate payment. So, for example, they may value cooperation, reciprocity, or the growth of the total plot. The alternate payoff values shown in the figure here are utility values rather than dollar amounts. They assume that both players prefer the game to continue at every decision point. Under these preferences, backward induction leads to each player putting the $2 in the pot, and the game continues. You notice I have 1, 1, 2, 2. So it always looks better, again, assuming each player does this analysis with these alternate payoff values. It always looks better to put money into the pot because it keeps growing. So we've just changed the payouts to not be the immediate amount of money, but sort of the relative value of putting another $2 in the pot, knowing that eventually when you get to the end, you get this larger payout. So that's the lesson here. I guess it's not so much at the backward induction field. It's more of the issue is that how you set the values of the payoffs. If you strictly look at the immediate amount of money, if the game involves money, you can get it wrong. You want to really look at the relative utility of the payout for each player, keeping the whole game in perspective. So I have a little bit here. The broader lesson is that the predicted outcome depends on how accurately the payoff values represent the player's actual preferences. And of course, they'd like to get to this biggest payout at the end. The study of such social and psychological influences on decisions is something called behavioral game theory, and I'll give you a reference to that. Okay, so this is the end of the lesson. It's the end of this playlist on game theory. If you like this lesson and if you like the playlist, please give it a thumbs up and consider subscribing to my channel. I have another set of lessons on stochastic processes. At the time I'm recording this, I've done 2 already, but I plan to have roughly another 10 on that topic.